So in this video, we'll be going over the sequence of real numbers. So let's start with an example. Let's say we have the series or the sequence of 2, 4, 6, 8, 10, and so on until infinity. Now we can call the first term a of n, second term as a of 2, third term as a of 3, and so on. And we have a general formula for any nth term of the sequence to be a of n, which is denoted by nth term, is equal to 2 multiplied by n. And this is the value of that nth term. And if we try to find a of 4 here using the formula, a of 4 will be equal to 2 multiplied by 4, which 4 is the n here. This is equal to 8, and there we go. So this is called a diverging sequence because we are going to infinity, and if we add all these terms up, we will definitely get infinity. So this is called a diverging sequence since you are slowly increasing. And let's say if we even have 1, 2, and we are increasing by 1 each time, and this goes to infinity, this means that it is a diverging sequence. So now let's look at another sequence over here. It's similar but different. 1 over 2, and then we have 1 over 4, 1 over 6, and so on. 1 over 8. And this sequence, the denominator goes to infinity. The sequence can be denoted by a of n, the nth term, is equal to simply 1 over 2n, right? Let's say if you want to find a of 4, which is 1 over 8 here, a of 4 is equal to 1 over 2 multiplied by 4, which is 1 over 8. So that's there. And this sequence here is called a converging sequence, since each time we add or we divide it by 2, we are slowly approaching 0, right? 1 over 16, and then 1 over 32, and so on, and slowly we will eventually reach 1 over such a large number that it will be like infinity. And 1 over infinity, we know that it is 0. So that's why this is called a converging sequence. And normally what we do is we find the limit. So limit of a of n, so the nth term where n is approaching infinity, and we find if it converges to a number. So let's denote it by L, where L is a number, so it is called a converging sequence then. And if it is not equal to L, so let's say we have positive or negative infinity, then it is called a diverging sequence. Now we could have indeterminate cases such as, let's say, 0 over 0, or we have infinity over infinity, or we have let's say 0 over infinity. So what should we do in these cases? We will use the L'Hopital rule, and I did make a video on it, so if you want to check that out, you can. So whenever we have this type of cases, we can use L'Hopital rule to check the limits again by deriving the numerator and the denominator and then checking the limits again, and then we will get an answer. So now let's do an example. Let's start with our first example. So our first question is, we have a of n given to us. So a of n is equal to n minus 1 over n, and we want to find what is the limit of n approaching infinity of this sequence, n minus 1 over n. So the first step is to write the few first, let's say 5 terms of a of n. So a of 0 will be equal to 0 minus 1 over 0, which is equal to 0, right? Or sorry, the first term cannot be determined since it will be 1 over 0. So let's find a of 1. which is 1 minus 1 over 1, which is going to be 0. And then the second term will be a of 2, so it will be 2 minus 1 over 2, so that is 1 over 2, and then 2 over 3, and then 3 over 4. So you can see a pattern. We just keep increasing the numerator and the denominator by 1, and this goes on until we have I don't know what number. And as you realize, as we're getting bigger numbers, we are slowly increasing our number, and we are approaching 1, right? So this would be like 99 over 100, and then 101 or 100 over 101, and so on, right? So we're getting very close to 1 here. So if we put the limit here and use direct substitution, we will get infinity minus 1 over infinity, and this is infinity minus 1 is infinity, since infinity minus a finite number is still equal to infinity over infinity, and here we are stuck, right? We cannot simplify this. This is one of those indeterminate cases that I showed you. So here what we need to do is we need to use the L'Hopital rule. So erase these, direct substitution, and what we have over here is n minus 1 over n. And what is the derivative of n here? Of the numerator is going to be 1, and minus 1, the derivative of any constant is 0. So that's, I'm not going to write that again. So n here again is going to be 1, and this is equal to 1, right? So the final answer over here will be equal to 1. So in question 2, we have the nth term of 4 minus 7 n to the power of 6 over n to the power of 6 again plus 3. And we want to again find the limit n is approaching infinity of this a of n. So how do we do that? Now there is a quick way. So whenever you have the powers of n the same, let's say we have 6 here in the denominator and 6 in the numerator, there is a very simple way. So what we can do is we can take the highest power of n here, it's n to the power of 6, and we take the coefficient of that n power. So the leading coefficient is negative 7 over the leading coefficient in the denominator is, if I write 1 over here, it's going to be 1, and the final answer here is negative 7, and this is the answer. And this only works if the power of n are the same in the numerator and the denominator. So in our last example here also we had the same power, right? So this is n to the power 1 and this is n to the power 1, and if we take the coefficients, the leading coefficients is going to be 1 over 1, which is 1, right? And the answer that we got is 1. So same thing over here. So again, let me warn you again, this only works if the power of n here is the same, and whatever coefficient you have, 7, negative 1, and 2, and so on. So if you think about it, let's visualize this. We in our both cases we will have infinity over infinity, but we don't know which infinity is increasing at what rate, right? So if the power of n is the same, we know that it is increasing at the same rate, and all that makes the difference is the coefficient of n over here. So that's it. So that's the answer for this question. So let's move on to an example where we have trigonometry in our question. So question 3, we have a of n is equal to cosine of n pi, close brackets, and then over n. And again we want to find the limit of n approaching infinity of a of n. So how do we do this? First step again is to always write the first 3 or 4 elements of the series or the sequence that you have. So a of n 1, I mean to say, is equal to cosine 1 pi over n. So it's going to be cosine, negative 1 over 1, and Next one is going to be 1 over 2, and these you can do just substitute on your calculator. 1, 2, and then n, for n I mean to say 3. And if we keep continuing, it will be negative 1 over 3, and then 1 over 4, and so on. So if we divide this now, let's see what is the behavior of the numerator here. The behavior of the numerator is simply gonna be either positive 1 or negative 1, right? Since no matter what you substitute n as, the largest cosine can be is 1, and the smallest cosine can be is negative 1. The range is between negative 1 to 1 basically. And in the numerator, if we notice, we are having an n, and n is approaching to infinity, right? So n here in the denominator is going to be over infinity. So we have basically plus minus 1 over infinity, which is equal to 0, as any number divided by infinity is 0. So this is a converging limit. Let's move on to another question where we have ln this time. So question 4, we have a of n is equal to ln n over n here, and we again want to find the limit of n is approaching infinity, a of n. So let's write this down. We have actually ln n over n, and if we use direct substitution over here, we'll have ln infinity over infinity, and ln infinity is infinity over infinity. So we have one of the L'Hopital rules here, or cases I mean to say. So what we need to do is we need to derive the numerator and the denominator. The derivative of ln n is simply 1 over n, and the derivative of n is 1. And if we simplify this, we will get 1 over n. And now if we take the limits again, as n is approaching infinity, we'll have 1 over infinity, and this is equal to 0, and that's it. So this is a converging sequence. And you might be confused when to use L'Hopital rule or when to use the leading coefficient. So if I go back to that leading coefficient example, right over here, we have negative 7n to the power of 6 over n to the power of 6, right? So if we use L'Hopital rule here and we derive 6 times, it will be negative 7 multiplied by 6n to the power of 5 over n, 6n 5, and the coefficients keep cancelling out until we are left with 7n, negative 7 n, and then over n, and then one more time we'll derive it since it's still infinity over infinity, so it will be equal to negative 7, right? So basically what the leading coefficient rule or the method is, just taking the coefficient, since we're going to derive it 6 times and we're still going to be left with the same answer. And of course here in our question 3 we had a cosine, so we cannot use that leading coefficient way, and in our last question we had a ln n, so we had to use L'Hopital rule. So again, remember, whenever we have infinity over infinity or 0 over 0, we use L'Hopital rule. So now let's move on to more complex examples, and I would need your full attention. So in our question 5, we have a of n is equal to n plus 1 over n minus 1, close brackets, to the power of n. And we again want to find the limit of n is approaching infinity. So if we use direct substitution, we will get infinity plus 1 is going to be infinity, infinity minus 1 is infinity, to the power of infinity. So this is one of the indeterminate cases, right? But we cannot directly use L'Hopital rule, since we can only use L'Hopital rule if you have infinity over infinity or we have 0 or infinity. The only issue that we are having here is that it is to the power of infinity. So somehow we need to convert this fraction with the power into a fraction. So we can use our rule again. So what we can do here is we can introduce a ln so that we can use the ln properties to bring the power down as a coefficient. So here I'm going to equate the answer. Basically what we need to find is y, right? So what I'm going to do is I'm going to introduce a ln both sides. So ln y is equal to a of n. So a of n is this part, and if I write here ln of n plus 1 over n minus 1 to the power of n, and now we can bring that to the power of n down since it is one of the ln's property. So let's say if you have ln a to the power of b, we can bring b down, and it will be equal to b times ln of a. So remember the properties of ln. So here what I'm going to do is I'm going to leave this part for now and just simplify this on the right hand side. So it's going to be equal to n into ln of n plus 1 over n minus 1 close brackets. And let me actually write this more distance. So now we need to somehow convert this into a fraction so that we can use L'Hopital rule. So what can we do here to be able to do that? One thing that we can do here is we can write n as 1 over n to the power of negative 1, which is the same case, which is equal to n, but we want a fraction to be able to use L'Hopital rule. So if you're not, I did explain all this in my video on L'Hopital rule, so you can check that out, but this is pretty basic stuff. So we convert this into, so our next fraction will be equal to ln of n plus 1 over n minus 1 and everything over n to the power of negative 1. So now we have a fraction so that we can use L'Hopital rule. So let's derive the numerator and let's derive the denominator. So the derivative of ln here is, let's say we have ln u is equal to the derivative of u, which is 1 over the same thing, so it's going to be 1 over u. So here's the same thing. We need to use coefficient rule though for deriving u since it's a fraction. So it will be equal to it was u v prime minus u prime v, I think. Yeah. So here it will be equal to n minus 1 into the derivative of the numerator, which is 1, minus, now we write the other way around, so n plus 1 minus the derivative of n minus 1, which is 1, multiplied by, here it is supposed to be everything over u, which is u here is n plus 1 over n minus 1, right? So here what I'm going to do is I'm going to flip it again so that I can times it, or maybe we can write it over n plus 1 over n minus 1 and then bring n minus 1 above, and it's the same thing. But here, just not to complicate anything, I am going to write it in terms of multiplied by, I'm just going to flip it directly. So it's going to be n minus 1 over n plus 1. And one thing that I forgot to add over here for the coefficient rule is it is over the denominator squared. So here is n minus 1 squared. So remember all your formulas, and that's it. Here I'm going to write this part over n plus 1 and everything again over the derivative of n negative 1 is going to be negative n and negative 2. So here, if you're getting confused, let me write the coefficient rule. So the coefficient rule goes over, let's say if we have u over v, it is simply v u prime minus u v prime over v squared, and that's simply what we did over here. So basically u over v is equal to, sorry, let me write it over here, n plus 1 over n minus 1 prime, and here we have prime also, and that's basically what we did over here. And the last thing which you might be confused is how do we get n minus 1 over n plus 1? So what is the derivative of, let me write it over here, or you know what, I'll leave that over there. I'll write it here. So if you're finding the derivative of ln x, it is 1 over x, right? So here we were finding the derivative of ln n plus 1 over n minus 1. So it's gonna be ln of n plus 1 over n minus 1 is equal to 1 over n plus 1 over n minus 1, which is equal to n minus 1 over n plus 1, basically. And that's exactly what we did over here. That's why I directly flipped it. So that's how we got that. So now let's start simplifying our answer. So let me just erase all this. We notice that we have n minus 1 here, and we have n minus 1 squared, so we can cancel one of them here. So we will be left with this over here. And let's simplify this part. So n minus 1 multiplied by 1. And let's open the brackets. So here we have n minus 1 minus, and this is also n plus 1. So it's going to be, we have a minus sign over here. So it's going to be minus n minus 1. So n will cancel out with n here, and we will be left with minus 2. So this entire thing can be replaced with minus 2. So now let me write the next simplified fraction. So we have equal to negative 2 over n minus 1 into n plus 1, and everything is over negative n negative 2 squared. And let's now simplify. Let's bring this above. So we will have limit of, and I'm going to cancel out the negative sign here since we have 2. So we have 2 over n minus 1 into n plus 1 is n squared minus 1 squared. So that's going to be there, multiplied by, now I'm going to bring n negative 2 above. So it's going to be n squared over 1. And we can simplify this again and write 2n squared over n squared minus 1. And here we have the limit. So limit, let me write limit over here. N is approaching infinity, right? And here we can take the leading coefficient of the two powers. So it's going to be 2 over 1, which is the final answer is 2. Now don't forget that this entire thing is equal to ln of y is equal to of 2, basically, since we evaluated the limit and we got 2. And we are trying to solve for y here. So here we need to get rid of this ln that we introduced. So how do we do that? We can introduce a e now. So it's going to be e to the power of ln y is equal to e to the power of 2. And here e and ln cancels out, so y is equal to e to the power of 2. And that is the final answer. And this will be a converging limit. And again, whenever we introduce ln, we always need to cancel it out, by using a e. So here we stated that we introduce a ln to be able to bring this n down. So in the end, don't forget to introduce a e to whatever answer you got. So we got 2 here, and to be able to find y over here, basically we need to introduce a e, and ln and e will cancel out, and we'll be left with y, which is equal to e to the power of 2. And that is a finite number as an answer. Now let's do an example with factorial in our limit. So let's say we have the sequence a of n is equal to e to the power of n over n factorial. Now if you don't know what factorial is, let's say we have 3 factorial. This is equal to 3 multiplied by 2 multiplied by 1. And let's say if we have n factorial, this is equal to n multiplied by n minus 1 multiplied by n minus 2, and so on until we reach 1, which is n minus a number is equal to 1. And we don't know what is n over here, so we have to guess. And one thing that you need to keep in mind is a factorial is more dominant or more it increases at a faster rate than a base to an exponential. So basically exponential function which we have over here, e to the power of n, more than exponential. So what I mean by that is, if you try to substitute, let's say, a few numbers and notice the behavior of these two functions or numbers, e to the power of n and n factorial, you will slowly realize that n factorial is going to increase at a way faster rate than e to the power of n. So just try substituting, let's say, uh, let me try doing e to the power of 13 over 13 factorial. And let's see what answer this gives. And you can try this on your calculator. So it was e to the power of 13 over 13 factorial. And straight away you can see that I got 7.10 and a lot of decimals multiplied by 10 to the power of -5. So we notice that this is approaching 0, right? And the bigger numbers for n that you substitute, you will get even more smaller numbers as answer. So one thing to keep in mind is factorial is a more dominant function than exponential unless you have, let's say, n to the power of n, which is like the base here is n, which is increasing. In this case we have e, which is a constant, right? So this case is even more dominant than a factorial. So if you have n to the power of n over n factorial, the function in the numerator is more dominant. So here this will be equal to infinity. And in our case, let me write both of them actually. Let me erase all this. So we have limit n is approaching infinity, and we have e to the power of n over n factorial, and this is equal to 0 as explained before. Factorial is more dominant, and this means that this is a converging answer. And let's say we have limit of n is approaching infinity of n to the power of n over n factorial. Now this is equal to infinity as n to the power of n is more dominant or increases at a faster rate than n factorial. And you can try numbers over here. So dominant, and this is a diverging answer. So as always, I do have a shortcut method for you guys. So for any limit questions, so let's say we have this question, n is approaching infinity, what we can try doing is we can substitute numbers for n here and try and see what the answer is approaching to. As I mentioned before, e to the power 13 over 13 factorial is very close to 0, and you can try e to the power of 15 over 15 factorial, and you will see that it is even more closer to 0. Hence the answer is 0. And in our last question, for I think this one, question 5, we had n plus 1 over n minus 1 to the power of n, and here we are approaching n to be infinity. So let's try to do this example with our shortcut method. So here first I tried, let me see what I tried, yeah, 99 for n here, and I got the answer as 7.38. Now when I tried the answer n as 999, I got the answer of 7.389. So we are very close, or we are diverging to an answer, right? And the answer that we got over here was e to the power of 2. And if we check that out, what is e to the power of 2? It is basically 7.389. So this is a way that you can quickly see what the series or what the limit is approaching to. And you can try different numbers. You have to try a very large number, also a very small number, and so on. So that's all for this video. I hope that you understood this topic, and if you have any questions, you can always ask them in the comment section. I'll be more than happy to answer. And I'll see you guys next time. And thanks for watching.